The checks effects interaction pattern. So this is really kind of interesting because it is just basically a technique to prevent unexpected execution of your contract. Now this is going to happen eventually at some point. They'll have an order of operations that ends up being in the wrong place. Something else happens. But if you use this process in that programming, you make sure that all of your prerequisites are checked off before a feature is executed. And so if you're like moving money from point A to point B, you want to make sure that A has got enough money to move to point B. Right? If someone's won an auction and you have a high bid, that person actually has the money to do and be that high bid, or there's a way to fail back to other bidders in that process if the high bid for some reason doesn't work. And that's essentially what it is. Just making sure that all of the prerequisites are checked before a function is actually executed. The goal of this is basically to reduce that attack surface, that threat level of a contract, especially if it's making external calls that could hijack the control flow of the calling contract. And this is a really common thing, and that's why this is really kind of an interesting technique to work, because the Ethereum virtual machine, the EVM, does not support concurrency. So you can call an external address, you can transfer Ether to another account, but that also transfers the control flow at the same time. Your external entity, that external contract, now controls the flow of the contract and can execute any inherent code inside of it. Or it can throw it off to somebody else. Or you can start going layers deep and get into a lot of trouble with this whole process. Now, most of the time, it's not going to cause any problems. Good contracts are acting in good faith. We really want to trust each other, but we're humans, and sometimes called contracts will act in bad faith, or they'll act and run malicious code, or they'll return it an unexpected state, or they'll do something that will blow up your contract. And that's an example of a re-entry attack in a nutshell, right? It's a malicious contract that re-enters your initial contract before the initial instance of that function is completed. So I call the bank, 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 move all that money out. And then I check to say, oh, is it completed? Yes. So we start stacking this up, and before I know it, my pool, my money is gone. Now, this is a real common thing. If you go and you take a look at the attacks listing, right, that this is basically used to call functions repeatedly that should only be called once. We've seen it in the real world. We've seen it in the DAO exploit. So it's all there. And if you're unfamiliar with smart contract development, this is one of those things that's really good for you to know about, especially as it's not sometimes in other software environments that programmers may be used to. Now, there's really two big problems we're trying to solve here. One, if you have hand flow control over to another program, or you want to make sure that re-entrancy attacks cannot take place against your contract, which is legit, right? Re-entrancy attacks will just kill your money all the time really fast. Now, where this generally happens, right, is when we're moving value from one person to another person, or from contract to contract, or from contract to person, right? It can also happen when you're checking Oracle data, and we've seen this in some of the other attacks where we get in place of that Oracle and we're able to give that Oracle data a wrong amount, right? So we also not only have a single point of failure, but I can input bad data into the contract flow. And then other places where flow control is handed off to another contract. You really do want to make sure that wherever you're handing flow off, that you know which parts of our function are susceptible to this kind of attack, right? And that's why implementing the check effects interaction pattern requires this as part of the process. So when you get into flow control of your contract, the programmer can take appropriate action when identifying all of the external calls that have control flow insecurities. And again, this is the idea of know your neighborhood and know everybody that you're interacting with, even if it's your own program. What makes this even more interesting is if you're in a consortia network, public, private, or fully private, among a number of institutions, and that you have all these things that may move in between institutions for external calls and can really screw up your flow control. Now, the other thing that's interesting about this is that state variables really matter here, right? These feature prominently in the effects interaction pattern. Re-entrancy attacks come back into the contract as a function call before the function is finished the first time, right? So to fix that, the program should not make any changes to the state before the call has finished and validated. And this is where you go through that process of checking, verifying, and if on air, try catch. Do the thing you need to do. So a big example of this, right, is if you're going to do a value transfer. All right. In this case, as a pattern, we only reduce the balance of the contract before the money is actually transferred. So we'll check it and go, okay, he's got enough money. So we're going to put this little side variable over here that we have the money, right? And then we're going to try to transfer it after that. And this way, if the transfer goes wrong, if we get an error, and we can just put that money back in the bank. We've never moved it. We're not going to lose it. We just want to make sure that we can actually transfer it. And if the transfer goes wrong, we can easily add that value back to the balance of the contract. If we error check to make sure that transfer went through, even if using a push over a pull for your transfer, right, you can revert the whole transaction and make sure that the state is accounted for as part of your error correction. And again, lots of cool things come back. You know, that false response back allows you to really work through that process of doing that error correction, error check without actually moving the money. If you actually do move the money, then you go and you commit to that balance reduction. If it doesn't go through, then you're pretty much so good to go. And you can do that all within the contract. Now, order matters here, right? Programs are pretty much going to work linearly. It's going to go through the process as you call them. The ordering of functions matters here, and the order of the checks matters here as well. So you have to be really intentional about what you do here, especially checking at the beginning of the process to be sure that the program or the person making the call to a contract can actually work. Especially if it's something like check balance, make sure there's a value available, or check this. If you're doing Oracle data, work with more than one Oracle. So if you have someone that's in there doing something squirrely, then you have an opportunity to weed that data out, or use an Oracle that has really good standing in the industry that's hard to hack, right? So only after you do all these things do you then check the internal state, make sure it's up to date, and then your call should be executed. So again, it's basically pre-staging everything. It's like if you're going to move into a house, right? You want to pre-stage the movers. You want to have everything in a box. You want to have all your books locked up. You want to have all of your TVs and everything else in your car. And that's essentially all it is. You're just making sure everything here is ready to go before you actually go do it. Now, the neat part is you can usually mapping. And again, mapping can be off-chain or on-chain data, right? So you can map that data like balance or current price by using requires and make sure that it's greater than or equal to whatever balance that you've got. So it's kind of a neat process where you can actually go through, map what you need to do, store it temporarily as a variable, and then go through that process of making sure everything is ready to move out of the house when you get to that point. So check effects, interaction patterns are really good for making sure of re-entrancy attacks not happening, right? In most cases, this pattern can be applied just by checking out the flow, right? And just check the flow, check what you've got, make sure you're getting back the expected things. And if you don't get back what you expect, throw an error. Error handling is a brilliant way of doing things, right? And any function that makes external calls should use this technique, right? They use this process. Regardless of whether you trust the party or not, just do it. Just get in the habit of it, right? Because even trustworthy parties can transfer control to a separate third party that you know nothing about. And again, we can nest these things down all the way to the point where you have no idea where on the internet this data or this reaction is coming from. And it could be malicious in the longer run. And that's all you're trying to do is just make sure that the data you get back is solid data that you really wanted to have. And if it's not, just make sure that you drop it or you do something, log it, maybe temporarily block the wallet. There's a lot of things you can do here to make this thing work. But again, the big goal here for this is just to make sure that you've intentionally thought out the flow of your program. You've made sure that if you're sending it off to a third party, external call, I think you've essentially got it covered from the idea of reentrancy, that we're checking all the things that we need to check. And that's it for this lecture. I'll see you in the next one.